For the following filter circuit shown, we're asked what is the magnitude of the transfer function V0 Vs at a frequency of 14.2 megahertz. We're going to use the RS and the CL given here, and so we have this right here. So when we look at this, we know that V0 over Vs is just our H of S. So this is the transfer function, right? H of S is equal to V0 over Vs, or Vi, whatever our input voltage is. And this is a low pass frequency, or it's a low pass filter. And the reason why it's low pass is because we have our resistor up here and our capacitor down here. That makes it a low pass. We've gone over this material, and that's in the playlist linked below the like button. Basically, we have some current flowing through this way. It's going to go through this way. All of it's going to make it over, or the majority of it's going to make it over this resistor and into this voltage right here. And when it is low, there is going to be 0 across here, and when it's infinite, when we have a lot, our voltage is going to be our same as the voltage source. Now that is just conceptual stuff, but we're going to look at solving the actual problem here. So to solve the actual problem, we can look at the notes that are linked below the like button, that are in the notes linked below the like button, and this is Engineering 17 Network Analysis notes, and actually it's EEE 117, and it's going to look something like this. So we have our R and our C just like this, and this is for a low pass. When we look at this, we can see that we have this derivation right here, and this derivation is from the node voltage method. It's super important to know that. And the node voltage method is when we have our voltage out, whatever voltage we want to look at, equal to our voltage source, and then we have our whatever impedance it's over, our voltage output is over on top. So here would be our capacitor, and then be divided by our R, so this resistor plus our capacitance. If we were to find the current, we would just switch it, and so we would use this resistor up top, and then we have both of these on the bottom being added together. So now knowing this, we can write the transfer function for this particular form, for this low pass, where we have our resistor and our capacitor like this. So the form for this is going to look like this. We just saw it. We're going to have our omega C over our S plus omega C, and those notes are very good to reference when we do problems like this. So now we need to find our corner frequency. Our S is going to be equal to our j omega. That's going to come in handy later. And then our corner frequency is equal to 1 over t. And this is not really t, this is kind of like t like this. It stands for the time domain. And we know that for a series RC circuit, which is what we have here, the time constraint is RC. So that means we have the resistor times the capacitor. If we had an inductor, it would be the inductor over the resistor. So we can rewrite this as our omega C is equal to 1 over our RC. And so this is kind of like the first step. Now we're going to rewrite this as the second step. So we're going to have H j omega, and this is equal to, and then before we do anything, we can notice that we're going to plug 1 over RC into both of these omegas. Well, that's going to be 1 over RC over S plus 1 over RC. And what we can do is multiply everything by RC. And then if we do that, we're just going to get 1 on the top. And then on the bottom, we're going to have S times RC plus 1. And now from here, what we can do is pretty simple. We're just going to substitute in for our S, the j omega. We already substituted it on the left, so we need to do it on the right. So we're going to have our j omega times our RC, and then we have this plus 1 here. So now what we need to do is find our omega. Well, our omega, we know we can use this formula, where we have omega is equal to 2 pi times frequency. And this is important because we were given the frequency right here. So really, inside of this omega, we're going to have 2 pi times 14.2, and this is being multiplied by 10 to the 6th, because that is what megahertz is. And then what we can do is we can plug this into a calculator. When we plug it into a calculator though, we're only going to want to plug in this part right here. That's the only part we want to plug in. And if we plug this in, the result that we're going to get is going to be our step 3, where we have our H j omega equal to 1 over, and we're just going to put the 1 out front. We have 1 plus our j times 1.11348. So that's if we plug everything that's underlined in green into the calculator. Now, let's note that this is the top and the bottom are both in rectangular form, and to divide things, we need it to be in polar form. So to have it in polar form, we're going to have the magnitude and we're going to have the phase, but we don't care about the phase here. So all we need to do is find the magnitude. To convert the top one, since we don't have an angle, it's just going to be the same out here for the magnitude with an angle of 0 degrees. And for the bottom one, to find the magnitude, because that's really what we care about here, we are going to set our v magnitude equal to the square root of our real number squared plus our imaginary number squared. And if we wanted to find this, the actual angle, we would have tangent -1 of our imaginary over our real number. So we would have something like that. And then if we were to do this for our value right here, we would get about 1.5 with an angle of 0 degrees. And so that means we would just have 1 divided by 1.5, and then we'd have 0 minus 0. And if we plug this into our answer, or into a calculator, we would get approximately 0.6682 as our answer. So that's how we would solve something for that, something like that. If we had something similar, we would just use the same thing, but combine the impedances with using parallel or series. And if we had something that looks similar to this, but not exactly like this, it could be a high pass or a band pass filter. So that's also to keep in mind because they have their own forms as well.